All right, let's continue with the last part of the chapter, transient stability analysis. Right. I think this is the going to be our last lecture to be in this semester, and then after this, we are going to have exercise sessions. Okay. Um, in transient stability, what we mean by stability, if you still recall from our first lecture, is that stability itself is it means the ability of the system, okay, to return to the equilibrium point or normal operating condition after the system itself is subject to disturbance. Okay, so we have to be clarified with this. So the keywords of stability is that, okay, it used to be an equilibrium point, okay, and then there used to be equilibrium one, and then the power system operate like this, and then there is a disturbance. So the disturbance, okay, will change the operating condition of the system. And whether or not, the stability is the study of whether or not the system, after being subject to disturbance, whether or not it could returns to the equilibrium again. Okay, after there is an equilibrium before the disturbance, and after subject to the disturbance, whether or not it would return to another, it could be another equilibrium. Okay, but normally it will go to another equilibrium, equilibrium one and equilibrium two. This is before and this is after, right? This is the meaning of stability. Okay, so the stability itself has different classifications, right? We have seen that we have three main stability problems, namely rotor angle stability, right, frequency stability, and voltage stability. So the what we are going to discuss in this lecture is it's on the rotor angle stability. So the stability itself can be further classified by the size or the magnitude of the disturbance. So we have classified that the stability itself, we have large scale or large disturbance, okay. And what we saw last time was that the equilibrium of rotor angle after the small disturbance. Okay, this is the what we have to recall from last time, right? So the small disturbance, the example, right? The examples that we have discussed in the small disturbance or dynamic stability, we call dynamic stability problem. Okay, the what was an example of what we discussed last time, right? We have considered the disturbance of introducing the small change to the state variable itself, is right. In this case, the state variable is it's a rotor angle or delta. Okay, so last time we have introduced the small disturbance to the delta. That was the first types of disturbance, as you saw from here, that we introduced the small disturbance. If the disturbance is small enough, then you could use the linearization technique, right? And from analyzing the system after subject to the small disturbance by using the linearization technique, you can see that the response or the response of the system can be classified by, can be split into two parts, right? The response itself is derived from the superposition of the initial operating point. Okay, this is the equation, the swing equation on the left. This is written in terms of the initial angle, okay, and initial frequency. Okay, this is an initial operating condition. And then after subject to the disturbance. So the linearization or the equation that describe the change of the rotor angle itself, it's from this linearization swing equation. So last time we saw that this equation itself is not sufficient because there is no damping term, right? If we proceed like this, you can see that the if you move this to the other part of the equation, you can see that there is no way that the rotor angle would be subside in the steady state. So we have introduced the what we call damping coefficient, so that the sum of this could be zero. Okay, so you can see that the if we sufficiently damp the systems, okay, so it means that there is no oscillation. Okay, so the characteristic equation is used to describe the behavior of the second order differential equation. You saw last time that we when we trying to deal with the second order ODE, right? What we have to do is that we convert the second order ODE into what we call the characteristic equation. Okay, this is the equation that describe the behavior in terms of the algebraic equation of the second order. Okay, and and we have discussed also that the technique that we could use to handle the second order equation in terms of in the time domain form, in the time domain space, right? The way that we could solve is that we could convert, right? We could convert the second order ODE into a system of first order. In this case, we are dealing with what we call state variable form, right? Or we could say that it is a space representation, or we are trying to represent multiple order ODE into a system of first order ODEs, right? So in this case, we will write in terms of the state space, right? The state space is, if you remember, x time is equal to ax plus bu, right? Where x is the vector of state variable and u is the vector of input variable. Okay. In this case, we don't we haven't introduced any input yet because on the right side of the equation, if you see, right, this is the system that the equation that describe the behavior of the system itself. For in this case, you don't have any input term on the right side. Okay, if you put the inputs on the right side, you have to write the state space in this form. You have to have u, right? Last time we saw that when we analyze the unforced state space, you can see that unforced in this case there is no u, or okay, there is no such terms bu. Okay, so we can see that when we want to analyze the behavior of this system, you can do it from analyzing the eigenvalue of the A matrix. Okay, or in order to solve this, in order to solve this system of linear equation, okay, this is a first order, so you could apply, right, the Laplace transform on both sides of the state equation, right? You transform this into Laplace, and since you have two variables, so you have to deal with the matrix operation. So you see that you can solve for it for xs in frequency domain, right? And then given this, you have to know the initial form last time, right? And then you solve for the delta s, delta in frequency domain, and you do the inverse Laplace transform to this, so you can get the time domain response. Okay, you can see that the rotor angle after the small perturbation or small changes in the state variable itself is you see, this is the initial condition plus this is the effect of the change of the rotor angle itself. So it would change based on the damping coefficient, okay, and other different parameters, damp frequency, natural frequency, etc. Okay, and the rotor speed, okay, will be deduced by, will be reduced by this term. You have this is the reduction of the rotor speed, right? And it's clear, okay, and you can see that the change that we have introduced to this is the delta delta, okay, delta delta zero, okay, delta delta zero. This is at any time function t after the introduction of disturbance. Okay, now we saw last time, right? This is the problem. We have introduced the small disturbance to the delta delta itself. I'm not going to discuss in the detail because we have seen from last time, right? So, but please remember that when we introduce the change to the generator, right? In this case, this is supplying to the load. Okay, so once you introduce the change, so the frequency of the entire system would be changed as well, because the frequency is related to the rotor speed. Okay, so the frequency can be determined by this equation, okay, by the rotor speed, and you change this from whatever we have radian per second, right? And we have to convert this radian per sec into hertz, right, in order to have the frequency. Okay, in this case, I think it's clear. Okay. Last time we derived everything in, you can further check, right? This is the equation, what I mean, right? This is you may wonder why F is used here, but if it's used instead of the omega, this is the rotor angle speed. You can convert the rotor angle speed to the frequency itself. So this is the after the disturbance. You can see that in this case the A matrix is, or the coefficient matrix is has an eigenvalue in the open left half plane, negative j plus and minus a negative 1.3 plus or minus j 6. This is on open left half plane, so this is a stable case from the control theory, right? And last time we also introduced the disturbance, right? In disturbance itself, we put the change of the power input by a small amount. That's why you see in this case you have the delta U in this case, right? So now after we did the same process, we we changed the second order ODE into state space form, and then we try to solve the state space the response in S domain, right? In this case, you see that we have basically two equations. Okay, we split the two equations into the state variable itself, the delta delta, and the first derivative of the state variable. This is the x2, right? X2 is the delta omega, because the differential of the rotor angle results in the rotor speed. Okay, so this is the response after doing the inverse Laplace transform. In these steps, you can see that the after changing the delta p, right, the rotor angle will change according to this equation. So we'll just deviate from the initial rotor angle speed, sorry, rotor angle, right, by the delta delta, okay, which is in a function of course, once we talk about the mechanical system, or it is a rotating system, you have to deal with the second order differential equation. So it is in terms of the multiplicative form of delta p. In this case, you can see we multiply this by delta p, right? Delta p is in the picture of this in these two equations, right? And this equation is basically, it's just substitutions of all the parameters that we have dealt with in the previous examples, right? You can see here that it is also a stable case due to the eigenvalue with negative real part, right? In this case, we have handled all the small signal small disturbance. Okay, so we are ready to discuss the what we call large disturbance. This is the topic that we're gonna deal with in this video clip. Okay. Last time we saw that if it is a small disturbance, you could you could use the linearization technique, and you could, split the swing equations into two parts, right? The first part is the initial operating condition, and the second part is the part in which the change in state variable will play the role. Okay. Um, this is the technique that when we introduce the large disturbance, that means that the what we call the linearization is no longer no longer applicable. Okay, this is the concept. The linearization is no longer applicable. So you have to deal with this equation by the time domain form in the way that you see when we have the second order equation like this, right? What we have to do is that basically we are trying to integrate both sides of the equation, right? When you do you do the integration, you can see that the equation after the integration is like this. So as you saw in this uh, in this by this equation, right? You can see that if the system is stable, okay? If the system is stable, what is this term would represent? If it is stable, means that after the disturbance, right, the system, the rotor angle or the rotor speed would be the same. Okay, there is no other acceleration or the deceleration. You can see from last time is that in the equilibrium point, okay, the concept is that at equilibrium point, okay, the property is that the PA has to be zero, because at equilibrium, okay, your rotor would neither accelerate nor decelerate, right? So acceleration and deceleration is not at the equilibrium. Okay, if it is still accelerating or it's gaining more speed, right, it means that there would be still some change required, right? In this case, if your rotor still accelerating, means that the mechanical power input is too much. Okay, so at equilibrium means that the PA is zero. The PA is zero means that the rotor speed in this case, okay, the rotor speed, because the delta by dt is the rotor speed. The rotor speed is zero. You may wonder why I see that why the rotor speed is zero, and you say that there's no acceleration. You see that you understand it correctly, by saying acceleration. For example, you are moving at 10 meter per second continuously, okay, without changing, with a constant speed of 10 meter per second, right? In this case, the acceleration is zero, okay, but the velocity is not zero, okay. But why can I say that if there is no acceleration, the d delta by dt is zero? This is correct, because you have to remember last time in our first lecture is that our delta here, it's the electrical degree that we measure with respect to the synchronous rotating frame. Okay, this is the measurement with respect to synchronous rotating frame. So what does it mean by that? If there is no change of the rotor angle with respect to the synchronous rotating frame, means that it goes along the synchronous rotating frame. So it is spin with 3000 rpm or 3600 rpms, right? So that there is no change in the delta with respect to time, right? Okay, so meaning that, if there is if the system is stable, means that this term d delta by dt has to be zero. You look from the right side of the equation. What happened? I mean, in which condition the right side of the equation would become zero? Now you see that the first, I mean, this factor is essentially some constant, right? Because it's 2 pi f0 divided by h. These are constants, so you get some constant term. The only possibility in which this whole square root things becomes zero is that the integration, okay, the integration of this part must be zero, okay. So this is the conclusion, right? The stability criterion is that the delta by dt has to be zero. That has to come from the integration of this term is zero itself. Okay, and this is clear, right? We have discussed that the relative speed of machine with respect to synchronous speed is zero. It doesn't mean that the rotor angle is zero. That is the lock rotor, it's different. Okay, if you say that it's I mean, stop moving, it means that you look from the fixed rotate, I mean, reference frame, right? But now the frame of reference is rotating, so it's a little bit different. Okay, and now you see that this term itself, the integration term, is the what we call the balance of the power. You can see that Pm is, if Pm is greater than Pe, right? Pm is greater than Pe, the input is greater than the output. So the rotor itself is accelerating. Okay, so in other words, if you have Pe less than Pm, right? Pe less than Pm. So you're meaning that the output or the requirement is greater than the supply, right? So the rotor angle would decelerate. Okay, so if we say that the integral of this is zero, means that the unbalanced power has to be zero. The unbalanced power in the sense that the difference between the Pm and Pe has to be zero. You can see from this. This is the first types of disturbance in the last scale, right? So you see that when we introduce a sudden step change. So the sudden means abruptly, right? Change in a small, little time scale, and there is a step change. So this is not possible to be a small disturbance because it's changed abruptly, right? We change the mechanical power input abruptly from point PM0 to PM1. We change this, from PM0 suddenly to PM1, right? This is of course, this is large disturbance, all right? So you can see that you will change the operating point from first equilibrium at point A to the next equilibrium point at point B, okay? Equilibrium point from A to B. So you see you have to deal with the balance of the power. If you go along this trajectory, you go you remember that this parabolic curve is the profile of electrical power output that is supplied from the generator to the load, right? This is from the E times V upon X sine of delta, right? Where the delta itself is the rotor angle, and which is the phasor of the E, and where we assume that the V is we connected the generator to the infinite bus. So the infinite bus here it's V and the angle of zero, right? So now you can see that this is the first the equilibrium point. You can take the notes here. This is from this point. This is equilibrium before disturbance. Okay. and this is the equilibrium point after disturbance. Okay, this is the equilibrium point before, and this is the equilibrium point after the disturbance. Okay, so you have to deal with the balance of the power. You would see from the picture itself that if you change along this trajectory from A to B, right? In this case, from A to B, the PM here is greater than PE. So you see PM is greater than PE. In this case, the rotor is accelerating. That means that acceleration means that the rotor absorb the energy, right? So it's not possible to maintain the stability because you receive more power than it is needed. So somehow in order to maintain the stability of the system, okay, if you have too much power, you cannot be stable. You have to release the energy somehow, right? So it would you know the it would have to deal with the another area, right, to balance out the power in this case, right? So the when we change the equilibrium point from A to B, it cannot go just from A to B like this, okay? It has to release the power out before reaching back to the B point, right? So the area of reaching, the area of releasing the power is the area A2, where in this case, if you move from this to this, you have too much energy, right? So you release energy, and during this, trajectory from B to D, okay. So during this time, your rotor would oscillate somehow before reaching the equilibrium point or another steady state. Okay, so by moving from B to D, you see that the PE is greater than PM. In this case, right, you decelerate because the electrical power needed is much more than the mechanical power input. In this case, you release the energy. Okay, so and soon after this, right, from B back to D, it's now it's stable. All right. So this is clear that the trajectory of moving between these two. Okay, if you integrate this curve between PM minus PE, okay, and you have this area. So this is the area in which you have mechanical power than the electrical power. So this is the acceleration area. Okay. And in this case, PM is greater than PE is greater than PM. So this is the deceleration. So the acceleration and deceleration must be maintained, must be exactly cancel out. Okay, if you have seen from plus and minus sign, then they have to cancel out in order to have no further acceleration. Okay, this is described by this equation, right? The area A1 is the acceleration area, and area A2 is the deceleration. Okay, so you see from this comment down below, 3 lines down below, is that the rotor angle will oscillate back and forth between delta naught and delta max. Okay, at the natural frequency, and if there is a damping present in the machine, right, this will cause the oscillation to subside and reach the steady state operating condition at point B. Okay. Now, this is the derivation that we have to deal with when you want to, the question to be answered for this kind of analysis is that how much we could further introduce the mechanical power to the rotor, right? How much additional mechanical power input that we could apply while we could still maintain the stability of the system. In this case, we want to examine how much my PM is, how much percent or whatever you can say, that how much power that we could increase from the initial operating point until the system, if we go beyond this point, the system will become collapsed. Okay. So in this case, you see that we want to find the PM, right? The way we find the PM is that we use the equal area criterion to establish the relationship between acceleration area and the deceleration area, right? So now you see that from this example, right? The rotor angle would oscillate back and forth between delta zero, delta naught, and delta max. So the first thing is that you need to determine the delta max first, right? This is the maximum rotor angle that the rotor, that the rotor could go, okay, and it will oscillate back due to from delta max back to the equilibrium point due to the damping. Okay, it will change from this rotor angle to this delta one by the damping. Okay, it will oscillate from this to this basically, right? And this is the now this is the the final equilibrium point at point B. So you have to deal with this kind of calculation, right? First step is that you from this equation we will try to determine the delta max first, and then you see that the delta max is the point in which it corresponds to the PM we are discussing, right? But this is not our new equilibrium point, right? The equilibrium point is here at point B, so you just step this back, by 180 degree, right? In order to get the same value, because this is the psi function. Remember, this is the P max sine of the delta, right? So if delta here, delta max is known, and this is equal to PM. PM is equal to PE, right? And you can derive for this delta 1, and soon after you know the delta 1, you can find the PM. So this is the steps, right? We are trying to find solving this the both sides of this equation. The first thing is that you derive for delta max. From this analysis, you see this is the equation that you have to deal with in this kind of an analysis, right? We are solving for delta max, but this is looking at this equation, right? You have one bad thing, okay? Because you see that the delta max here is in multiplication with the sign of delta max. Delta max times sine delta max. This is of course nonlinear equation. Okay, this is not a nice thing because it's hard to solve. Okay, so you have to use the iterative approach like Newton-Raphson to solve for the delta max first, and then soon after you know the delta max, this is step one. You find the PM corresponding PM, and you try to resolve the delta one, right? So this is the new equilibrium point, right? At this new rotor angle, right? All right, we take a look at example 11.4. Okay, this is a continuation of problem example 11.2. The machine is delivering real power at 6.6 and PU and 0.8 PF lagging to infinite bus. Last time we saw that we need to determine the internal EMF E, right? At the generator over here, E prime. Okay, let us take a look back. All right, we will go through first. The infinite bus bar itself is 1.0 PU and the angle here of 0. So we will determine the maximum power input that can be applied without loss of synchronism, right? In this case, it is the PM1 or PM. In this case, the problem asks you what's PM here, right? That's what we have seen. Okay, so in order to find this, let's recall the equation that we need to solve for the Pmax. Okay, so the equation that we use to solve for the delta max is this the nonlinear equation, the delta max minus delta zero. So the delta zero here is the initial rotor angle, which is the condition before the disturbance, right? So we need to find this initial angle first. Okay, remember from this is from the from problem 11.2, which is right here, the 11.2. We saw that the excitation voltage, the angle of the rotor angle is 16.79. So we have to substitute 16.79 into this equation here. So this is a 16.79, which is 0.2931 radian. So we substitute this in terms of radian because we are dealing with, if you deal everything in radian, of course, this should be in radian, right? Because you multiply a number with a sign value, right? And it is equal to cosine. So all the units of the rotor angle should be in radian. So, right? Because if otherwise, if you substitute this in degree, it doesn't make any sense because this is a constant value, right? Multiplied by radian. Okay, so that would become angle, right? In if it is in degree, then this is degree this term plus for this it is a constant term. This is unitless. This is the if you use a degree, right? You will get if you replace the delta in degree, this is degree time no unitless. There's no unit, and this is no unit. So it doesn't make any sense to combine this something like this. So the angle must be in radian in this case. Okay. So now you can see that in order to find the maximum power that you could supply, you could apply to the machine, right? So you have to solve this equation. Basically, delta max minus 2.9 times sine delta max here, it's a nonlinear equation. So in this case, we apply Newton-Raphson to solve for this equation, right? So this is a long process if you do by hand calculation, okay? If you do this by hand calculation, this is you need a lot of effort, right? So you have to solve this. Basically, you need to linearize this one, okay? And you need to find the delta max, okay? You need to organize this in the form of fx is equal to 0, but this is luckily this is just one equation, right? So you need to you have to define the delta max, right? This is a proportion. We have discussed this already, right? This is the divided by derivative. So it is from the Taylor series expansion. Fx plus delta x is equal to fx plus, right, df dx into delta x. Okay, so in this case you have the delta f and you plus with this guy. Okay, so this is since this is to be 0, this is equal to 0, is equal to 0. So in this case you want to find the delta x in this case, right? This is delta max, which is nothing but f of x divided by df dx. If it is in iteration k, and this is in iteration k, for example, this is the delta f at the iteration k. So you use this equation to update the value, right? So you update until you get this, right? You get this portion fx is close to 0. If you get this close to 0 or the delta x is close to 0, means that you arrive at the root of this fx equation. Okay, you arrive at the root of this nonlinear equation. Okay, So once you find the delta max, so you could find the PM, and at the PM here is 1.684 PU. That means that you could further increase the power from the initial point, as initial condition is zero point 0.6, and now you could increase the power input by 1.6. Sorry, there's a negative, a minus of these two. If you ask for how much we could increase the PM, right, the mechanical power, you could increase by 1.084 PU, right, roughly about almost uh, one per unit, 1.1 PU, right? This is how much energy you could increase. All right. So you have seen that you find the delta max, which is here, 125.84. Then you could find the new equilibrium point. The new equilibrium is here. So yes, you can find that the delta one here is the you just step back by 100 and um, is it yes, you could step back here, right, and you determine this by you can get this 54.16 degree. All right. uh, Nothing else. We Okay. I think this is clear by itself. And the problem B, question B said that to repeat the question A with the zero initial power input, right? And we assume that the generator internal voltage remains constant from the value computed in question A. So basically, when you start with the zero, um, let me see, the initial internal EMF E remains the same. So the trajectory of the E is the same in this case, right? The PE would be the same, okay? So you can see that this is 2.06 sine delta. So if we put this, you see this is the same PE profile. The PE remains the same, except the delta we start from zero. Okay. Now you can see that if you substitute this by zero, and you also apply the Newton-Raphson for to this equation to solve for the delta max here, which is 133.563. Then we determine the corresponding PM, the new PM over here, because you get the delta here and you get the PM, right? This is about 1.505. This is PM, all right? And then we can step it back and you find the delta one, which is the new operating condition, right, after the disturbance. So you see that during the disturbance, okay, the rotor angle just step back and forth, okay, until it reaches the new equilibrium point at this point. Okay, delta one at this angle 46.34 and the PM of 1.5. Okay, and this is to answer the question, right? So now in the section 11.6, we are going to apply another type of large disturbance. The previous disturbance was to introduce the sudden load increase, right? And we are trying to find how much the sudden load increase could it be before the machine would lose the synchronism, right? So now we will try to introduce, of course, when we say three-phase fault, meaning that this is the most severe types of short circuit to the power system, right? So the scenario is like this. We have the generator on the left side. The generator here is supplied by, during the normal operation, right? It is supplying the mechanical power input by the turbine. Turbine supplies the PM and the PE. If it is in equilibrium point, okay, the PM and the PE should be equal. That means that the rotor angle doesn't accelerate or decelerate, right? In that case, the power was supplied through the this transformer, and that is a two path, right? The power, for example, we will get 100, and if these two circuit, right, this is what we call double circuit transmission line. This is called double circuit. So you can see that if it operates normally and the line parameter of the two parallel paths are the same, so we assume that you see this is 100 flowing into bus 1, and if these two are identical, then the above and the bottom would, 50 would flow, equal 50 would flow on the both routes, upper routes and the lower route, right? If assumed that PM is constant and the generator is operating steadily, delivering power to the system with the angle of power angle of delta zero. Okay, and if there is a temporary fault means that it just happened to a certain short period of time. The three-phase voltage fall occur at the sending end of one of the circuit, right? At bus one, for example, at point F. Okay, temporary means that a certain period of time. It doesn't. It's opposite to permanent fault. Okay, if it is permanent, then it means that you would, if this is a permanent three-phase fault, then this line would last forever. Would be, we will lose this line forever. Then it's not possible to, if this transmission line could carry 100 megawatts, so this 100 megawatt will flow through the first path, right, the upper path, right? But if it is not the case, right, in the steady state, you will, the power transfer from the generator is limited by the power transfer capability between bus one and bus two, right? So we are interested during during short period of time, we want to see whether the generator will operate normally or not, right? Will it be able to maintain the synchronism? Would it be still intact with the rest of the system, right? This is our question. Okay, so we model this in terms of forward swing, right? In terms of, I will explain to you what we mean by forward. Okay, um, if we say from if we see from the power swing equation, or this curve PM and PE curve, right? So the initial operating point is at point A, all right. Then there is a transmission. The fault, three-phase fault occur at one of the trans of the line, right? It means that the current capacity, right? If that is the case, in this case, during this short circuit, right, the power would still be able to. The power will not be able to flow through the upper path, right? In this case, because if you can see that once there is the three-phase fault at the point F here, so the power will not flow in this way. Okay, the one I discussed was in the steady state. Don't be confused with what I'm discussing now. Okay, because if there's a short circuit here, okay, the current flowing direction would be going from the source and go directly to the ground, because this is easier. This path is easier for the current to flow, right? So the power or the current that flows out of the generator will not get into bus one and will not flow on from bus one to bus two, right? It will go, all will go to the ground. Okay, that's why you can see that from A, if it is the three-phase fault, then the power will flow, will become zero. The PE, electrical power that we go from here to here, this is PE, right? The PE that delivers to the load is become zero in this case. So this is the condition during which the fall happened, right? This is the duration in which the temporary fall occurs at the sending end of the line at bus 1. Okay, so during this time, you can see that the mechanical power is greater than the electrical power because there is not possible to it is not possible to transfer the power from generator to load. Okay, so the PE in this case is 0. So this area, the rectangle area here, represents the PE is greater than PM is greater than PE, which is acceleration, right? This is an acceleration area. Okay, in order to maintain the stability, you have to absorb the acceleration or this excessive energy, right? So there must be an area that will absorb this excessive energy. Okay, so the trajectory it would be like this. All right, so it would be the area A2. Okay, so during point B and C, this is the point where there is a fall, right? So PM is greater than PE, where PE here is 0. So this is an absorbing energy or acceleration. The generator just speed up, right? So if this fall is clear, then in this case, okay, the PM is still PE and the generator is still accelerating, right? So it goes to up to point D in this case. Okay, this is the point D. So, okay, it's a continuation. The point D will have to go to point E first, right? That where here, we have to go over the electrical path, right? The PE. Okay, so in this case, the D to E, okay, PE is increasing. Okay, so now in this case, the rotor still, in the decelerating mode because now at this point the PE is what is greater than the PM. This is in decelerating point. And then from E, right, they still decelerating E to F. Okay, E to F. E to F is PM is greater than PE. In this case, during this along this line, right, it just release the energy right along this line. So the generator will speed up at this period of time. Okay, now the generator will slow down during this period of time. Okay, they will slow down during this period of time. Once we reach the point F, right, we will have to go, to this point G, from F to G. Okay, you can see that at point F, delta 1 is equal to delta max, so this is the deceleration. So it would form, because the area that we integrate over the delta here would be represented by, during this change, right? The change of operating point, okay? The sum of the energy, okay? The sum of the energy will be the same for absorb energy and the release energy. These two must be the same, otherwise the generator would not be stable. Okay, this is called the forward swing because we you can see that the movement of the angle, right? We starting from the smaller rotor angle and we we go right where the angle separation just increase, so that's why we call the forward swing. So if for the backward swing, since we know that we discussed already that the rotor just oscillate, right, from one stable from one equilibrium to the other equilibrium. During this time, okay, the rotor just oscillate. There is an oscillation during this time, just oscillate back and forth, right? So you can see that the delta from the case that we discussed earlier will just keep increasing, right? We'll start with from the lower the operating or the condition with the lower rotor angle and the next equilibrium point, okay, which is in this case the delta one. The delta one here is the new equilibrium point. we have you know, the bigger rotor angle, right? So the backward swing is opposite. Okay, we will start with the bigger rotor angle, and the new equilibrium point is the less the rotor angle. Okay, the less rotor angle. Now you see, we start with the delta zero, and the new equilibrium point is at delta two, right? It is possible also in this way because the rotor angle will oscillate back and forth around the delta zero at natural frequency. So due to the inherent, okay, damping ratio, the oscillate is back and forth. So it's possible that, you know, the new equilibrium point would have the less rotor angle. Okay, so in backward swing, it is the same, right? The trajectory or the change of operating point can be seen from this graph as well. You can see that we have both release energy or the decelerating area, and the area in which we have the rotor acceleration, or in this during this time the rotor angle just absorb the energy. Okay, so release and absorb is if this release and absorb energies are the same, then uh, the the rotor angle is stable, right? So the criteria that we want to see is that how much the rotor angle, I mean the critical clearing angle, okay, how much the rotor angle could be separated from the initial operating point before the generator will lose the synchronism. So we are interested in determining the critical clearing angle, or delta C, right? In this case, we are interested to find how much the critical clearing angle is, okay? Which is the angle, critical clearing angle delta C itself is defined by the maximum clearing angle that the stability margin area is fully used, okay? It's fully used means that the acceleration is equal to deceleration, and the system is still stable, right? It's still stable. Well, in this case, this picture is particularly for the case of three-phase fault, because during the disturbance, right? In this case, the PM becomes zero. Okay, the PMs become zero. Okay, now you can see that if the PM becomes zero for the area A1, you can see that there is no PM in this case, because this is integration between PM minus PE. So the PE here is zero. Okay, the PE here is zero during this area. Okay, you should link between these two. Okay, we integrate from the delta zero to delta C from this point B to C, and if we find area under the curve, okay, and area A2, okay, in this case it is the, you know, PE is greater than the PM. This is the deceleration area. Deceleration area in this case, right, it is PE minus PM. PE minus PM. Okay, luckily you. So in this picture, we are trying to, you know, as we discussed earlier, that from this picture we are trying to find the delta C. In this case, the delta C is defined by the maximum, I mean the critical clearing angle, or critical clearing fault angle, right? Delta C, which is defined by the maximum clearing angle that the stability margin area is fully used. You can see that the original equilibrium point is at point A, right? When there is a short circuit happen at, for example, here the fault circuit is at the bus itself, so that is not possible. I mean, the electrical power is not possible to flow through any of these two transmission line. It cannot go from source to the load, right? For during this fault, the electrical power is at zero. So we are interested at how much the critical angle could it be during this time, right? So basically, if the stability is maintained, meaning that the synchronism of the synchronous machine is still maintained, right? Meaning that in this case, the acceleration area and the deceleration area should be equal, right? It has to be balance up the energy, right? So this is, in this case, this is accelerating and this is the decelerating area, right? So you can see that the integral of Pm, this is Pm, this is Pm here, okay, minus Pe, which is 0 in this case, because during the fall there is no electrical power transfer from source to load. Okay, and it is equal to the deceleration area on the upper part here. You can see that this is Pe minus Pm, right? So the Pe is up there. It's a parabolic curve, okay, which is P max. In this case, this is P max times sine of delta. In this case, the delta is the rotor angle, right? You can see that's Pm minus Pmax. So as you can see here, we are trying to determine the critical clearing angle. So it can be done by, in this form. Okay, in this case, the delta max is easy to find. We don't need to determine the Pmax like before. Okay, you remember in the previous example, we need to find the Pmax first. But in this case, the Pmax can be directly determined because the Pmax is the Pe corresponding to the Pm over here. So you can say you can determine the Pmax straight away from here. So from this equation, we are trying to determine the delta C, okay, and this is the explicit form. Okay, you can see that since we are trying to find delta C and you don't see any delta C in multiplication with delta C itself, so you can rearrange the equation somehow, right? So you can see that this is delta C in this in here, okay, and Pm delta C, and okay, also you can have the delta C right here and the delta C right here, and okay, the Pm plus and minus on both sides, these things can be cancelled. So is it right? Yes. So you can just find the cosine delta C, which is here. Okay. So you can determine that. But since we are in this picture, we're trying to determine delta C, but in reality, right, the delta C you cannot directly measure from the generator because there is no such a, it's not that easy to measure the rotor angle, okay, and when you set the protective relay, or when you deal with the protective devices, right, the key parameter that we are interested is that how much time, okay, how much time you could allow the three-phase fault to occur, right? So the delta C itself, it's not it's not a meaningful measurement. Okay, this is the key thing, is that it's not so meaningful measurement, or it's not a meaningful indicator. Okay, indicator for stability. All right, it's not a meaningful indicator for stability. Okay, we are interested to know how much time we could allow the three-phase fault to occur. Okay, so we are interested in how much time. Okay, time, it's easy to measure, right? How much time we could allow, okay, three-phase fault to occur. Okay, this is the concept. So we are trying to, to change this axis from the rotor angle to time, right? When we are trying to find the TC, which is the critical clearing fault time instead of delta C. So the critical clearing time is the maximum fault clearing time period to be unstable. Okay, that's why you can see that we draw another time axis. Okay, and we are trying to find the time from the time t0 at the initial ordering point, and we want to measure how much time we could allow during this time the three-phase fault, right, occur, three-phase fault, how much time the three-phase fault could last, okay, before the system will go unstable. Okay, so in summary, right, we once we know the delta C, okay, once we know delta C, you could try to solve the term, right? You can see that this is the swing equation. So whatever happens to the machine, right, it has to oblige, or the characteristic of the machine has to be characterized by the swing equation. Okay, so you can try to solve the swing equation by having said that, during the fall, because during this time the three-phase fall occur, right? So we set the PE to be 0. Okay, and we try to solve for the relationship between delta and t. Okay, this is the how we could do it. You just solve this second order different. This is the not the really second order, right? You can is this in explicit form? You just move the constant to the other side, and you integrate twice, so you get the delta. So this is the relationship between delta and t, right? What you will see is that once you know delta c, you want to solve for tc. So you know delta c, you want to solve for tc. This is pretty straightforward, right? So you just change you just subtract delta c by delta 0, and multiply by the inverse of this factor, right? And you take the root. So this is the equation that you uh, want to map the relationship. So I think you better highlight this one. This is the relationship that once you know the delta c, you want to know the corresponding tc. Okay, that because it's easily it is easier to measure, to measure the indicator of the stability in terms of time instead of the rotor angle. Okay, this is to show that what's going to happen when what's the interpretation of if you clear the fall before the critical clearing angle, right? You can see that this is in the first picture. Okay, if you clear the fall before the critical clearing fall time, which is at this position, so now you can see that at bus 1 and 2, right, the rotor angle is at the same position, because the delta is the same. Okay, and this is the relationship between this is the PE versus delta, right? But this is the the excursion of the rotor angle. At point 1 and 2, the position of rotor angle is the same. Once it undergoes the three-phase fault, in this case, right, you see that the angle separation is greater in this case. It's going to a bigger value in this case, right? And at this point, at the operating point 3, 4, 5, you got the same, right? The same delta, because it's on the same axis over here. Okay, and your as we discussed earlier, during this movement of the operating point, right? The swing, the rotor angle would oscillate back and forth, right? This is to show you, the excursion of the rotor angle that swings back and forth. Okay, and you can see that in this case, the rotor angle just further. In this case, this is the acceleration and this is deceleration. Once it's decelerate, right, it could also, go a little bit further, and soon after that, it would come back to be steady state, right? Because the angle separation from, you remember, this is when you measure with respect to the synchronous rotating frame. Okay, meaning that if it goes like this, the separation is greater, right? It's going to be not so healthy for the generator, right? Because the maximum angle would be 90 degree. Okay, if you still recall that, you can see that the angle separation is tends to be smaller, right, towards the new equilibrium point, right? Similarly, you can see that if we clear exactly, okay, we clear the fault exactly at the delta CR, which is the critical clearing angle, right? So you see that the angle excursion at point 8 is a little greater than the previous case because you are moving to the limit, right? So the angle separation is becoming greater, and since it is stable, okay, the angle will tend to be back, a smaller value. Okay, that's why it calls it can regain the stability. Okay. And if we clear the fault at the time greater than the critical clearing time, or the angle, right? The angle, the fault clearing angle is greater than the critical clearing angle. You see that the rotor excursions tends to be, apart from the initial operating condition, right? So you can see that once the time goes by, the rotor angle will further, up be you will be further go away from the synchronous rotating frame. Okay, so this is becomes unstable. All right, uh, just like when we compare with the horse pulling by, pull the cart, pulling the cart, right? If you lose the stability, means that the some of the horse will be probably, go away from the group, right? Now we were talking about the second case of the three-phase fault. In this case, the scenario is a little bit different from the previous one, whereby the previous one we consider the occurrence of fault at the bus itself. In that case, in the previous case, if we have introduced the fault at the bus, right, there is no power to flow from the source to the load, because once the power goes in from the generator, right, it will go directly to the ground without the transfer from the source to the load, right? But now the location of fault changed to the middle of one of the transmission circuit. For example, it goes to, maybe it's a midpoint, okay, or it can be some distance away from bus I. So in this case, okay, it's a scenario is different, because it allows some power to transfer from source to load, because you know once the power goes in, this is during the fault, right? And there is a way, okay, that the power could flow from the bus one to the point of to the ground over here, to the fault location. Okay, and during the fall also, the power could be transferred from one end, from node 1 to node 2, because it can flow in the upper part. Okay, but now during the fall, you could transfer less power, because you can't carry the other power through the lower path, right? So in this case, okay, the during the fall, okay, the electrical characteristics or power transfer characteristics before fall, during the falls, and after the fault would be a little different. Okay, so we can model the power characteristics by the following picture, right? So the initial operating point is at A, okay, and once there is a fall happening at some distance apart from bus one, so you can see that it the power could transfer from the source to the load because the PE, the electrical power here represents the power transfer from source to load, right? So there is some power to flow from source to load. That's why, but of course the magnitude should be less. Okay, okay, the magnitude should be less because you remember this is E times V divided by X and sine of delta. During the fall, the X here will be increased because you lose one of the transmission path. So once your X increase, then the P max, okay, during the fall the P max will decrease. The whole thing, I mean the whole factor will decrease. So this is the PE during the fall, model like this. So during the fall, instead of, if the fall is at bus one, you remember, the PE is zero. In this case, the PE could still be transferred, right? So it will go along this trajectory during the fall. This is of course, in this case, the PM is greater than the PE, right? So this is the PM is greater than PE. This is acceleration area, whereby you cannot allow just the rotor to accelerate. Otherwise, it will not be stable, right? So there is another decelerating area. So the deceleration area is obtained when the fall is clear, right? When the fall is clear, it would follow the other trajectory. So it's just the so-called PE after the fault. Why is it after the fault? It's different from PE before the fault because the this factor, the P max would be different. Okay, if you change during this time, right? If your E and your V change, your magnitude will be changed as well. Okay, so the PE after the fall is not necessary to be the same as the PE before the fall because you disturb the system and it may not be able to be at the same point. Okay, just like when you have your own your own life, right? You are disturbed by a certain problem, right? It's maybe not possible for you to return to the point you were before the disturbance, right? For example, if you break up with your girlfriend, right? Some of you, maybe you cannot return to your the condition beforehand, right? Is the same in this case. So the decelerating area, you have to follow the PE has to follow the trajectory after the fault. Okay, we will see, how to define, this. How do we find the curve B and C in this case, right? So the PE beforehand remains unchanged from the previous case because you didn't introduce any disturbance at the curve A, right? What we are interested is that we are trying to see how we're gonna deal with the curve B and C's. Okay, the same line of idea, right? We are trying to determine the new operating point in this case, right? And if you are trying to find the critical clearing angle, right? In this case, we want to see how much the rotor could go before the generator would lose the synchronism. So we are trying to find the what we call the stability limit, right? Well, in this case, the stability limit can be determined by the P max here will go to this point, right? So the P max here, it's determined by it's determined from the PE after fall because you see that the decelerating area. So the after the disturbance, during the fall, the generator will accelerate. You can see from this case, this is during the fall, right? This is the during the fall. Okay, just like you're trying to disturb the system. So the rotor is spinning, you disturb it. During this time, the rotor will speed up because the PM is greater than PE, right? So this is the speed up or accelerating. Okay, physical meaning is in this case is speed up. But in order to be stable, it has to slow down, right? So the slow down event, okay, it has to be after the fall. So the trajectory of PE that corresponds to the deceleration, right? Decelerating area, okay. And this during this time the rotor motion slow down, right? That the situation is must be after the fault. The situation must be after the fault. Okay, so the point, the delta max here could be determined that by solving the PM, which is the input, right? And this is the PE after the fault. P after the fault, you have a certain function, right? And you substitute the PM equal to the PE after the fault, and then we're trying to solve for the corresponding delta, right? That corresponding delta results in the delta max, right? And then you could use the equal area criteria to determine the delta C. So the delta C here can be determined by the equal area criteria, right? Equal area criteria. Okay. So in summary, I would say that this is the first step that you need to determine first in this case, right? And in order to solve for the delta C, this is the second step. Okay. And what should be the third step? Okay, the third step is to transform the delta C to TC normally, right? Because we are not interested in knowing the delta C because it's hard to measure, right? And it is not the meaningful indicator as well. Okay, so please see the steps. All right, what I'm discussing here is to explain to you the step of the calculation. So look at the purple color, right? The step 1, 2, 3, and you follow this, and you will not get lost during the way. Okay, so you see you can equate the area A1 and area A2, right? In this case, I mean everything is all the parameters are known except delta C, which are the point which are the unknowns, which is the unknown, right? Now again, you see the PM can be cancelled, PM delta C can be cancelled on both sides of the equation, and what is left is the delta C, which happens in this at the bound of this integration. So you just integrate this guy, okay, and not that difficult, right? It's not a difficult integration of at all because this is a constant multiplied by the sign of delta, right? So this is easy. This is the easy integration. So you can just remove this and this is delta C. Okay, we are trying to solve delta C, and this is the explicit formula. Explicit means for those who are not you don't who those to those who don't understand what explicit it means that the equation can be directly determined that, right? It's easy, it's clear, right? We can just substitute the value on the right side, and you take the inverse cosine to get the delta C. Okay, so this is the explicit form. All right, and again, this is the equal area criterion in case that the line is not connected directly to ground, or there are some possibility. There is a possibility of the power to be transferred from source to load. So we have the other two power transfer curve, right? Or power angle curve, which is the curve during the fall and the curve after the fall. This is during the fall. This is after the fall, right? And this is just like what we have seen earlier, right? In the case that if we clear the fault before the critical clearing angle, you can see that the excursion, the rotor angle excursion, is able to return to, I mean, it's getting smaller, right? In this case, but if you clear the fall a little slower, so during this time, the fall excursion, the rotor angle excursion is getting larger, but it would subside when the time goes by, because it can regain the stability. You can see that the trajectory is in this way. It's reducing. Okay, but if you clear after the critical clearing time, so you can see that the rotor excursion tends to be uncontrollable, or it's not going to subside, right? So you can see these are the to map the relationship from the power angle, okay, and the time excursion of the rotor angle, okay. This is the numerical example, right? I want you to just go see what do we mean by this disturbance. How can we deal with these scenarios, right? And I mean the the detail calculation, you can do it yourself. Okay, you could do it yourself at home. Okay, but I want you to see the steps and the idea, the logic behind, right? Now you can see that this is the example 11.5 in Hadisada. Okay, and 60 Hertz synchronous machine having energy edge at 5, direct axis, the transient direct axis is the reactance. Okay, zero point 0.3 per unit connected to infinite bus through the transmission circuit. Okay, double circuit transmission line. The reactants are marked on the diagram on the common base. The generator is delivering real power of zero point 0.8 pu and Q of 0.074 per unit to infinite bus at the voltage of 1 per unit. So basically, the loading condition of the generator, it's given, right? Or the supply condition, I have to say, the supply condition of the machine is given. Okay, so what you can see is that from giving this kind of delivering, right, delivering the load. So but somehow you could derive the for the current, and once you know the current, in this case, right, without further readings, right? You can see that given these two kind of explanation, right? The first thing that should happen in mind is that you have to be able to find current. Once you know the current, right? You know the voltage at this the infinite bus, okay? The, impo- the most important characteristic that we are analyzing is the rotor angle. Where is the rotor angle placed? It is at the internal EMF here, right? So what we are interested is the delta, okay, and of course with the E that as well, okay. So from this current, the current delivering, and you use the circuit theory, you know the V, and you can determine the E, right? For the problem A, if the temporary fault, so it will clear after some time, occurs at the sending end at point F. So this is the short circuit to the ground. So you can see that in this case, you have to think of the case one, where the electrical power during the fault is 0. this case. So you can draw, in this case, PE during the fault is 0. Okay, because there is no path for the power to flow from source to load. So the P electrical power during the fault is 0 in this case. When the fault is clear, both lines are becomes intact. Okay, and determine the critical clearing angle and the critical clearing fault time. So this is pretty straightforward, right? You just you think of this case, okay, that's not nothing we can discuss much about this case, because just the delta zero, you have to determine the delta zero first from the initial loading condition, and then the PM, the P max, everything, and you could solve for the delta C straight away, right? And once you know the delta C, you use this equation to convert delta C to the TC, all right? That is clear. It's not a big issue, right? The point B, the question B, is that the three-phase fault occur at the middle of one of the line. For example, the could happen just here because the two lines are identical, right? And the fault is clear. The faulted line is isolated. So the faulted line is isolated, meaning that what? Meaning that the reactance, right? The X after the fault. What is the X after the fault? I mean the transfer reactance. Now you know the transfer reactance, right? What I mean by transfer reactance. The reactance will be changed because the reactance between 1 and 2 after the isolation of the faulted line. For example, the lower line here, after the fault is clear, this line is isolated. Once this line is isolated, meaning that the total reactance from bus 1 to 2 will be double than before, right? Will be double because what? Before the fault, if there is no fault, right? The equivalent reactance between these two is 0.15. It's a half of this, right? So once you lose the upper line, the lower line, meaning that you lose this guy, so the total reactance will be zero point 0.3. Okay, it just becomes double. So as we discussed earlier, that when during the fault, this X becomes greater, so the PE, the total PE will become less. Okay, the total PE will become less. So that's why you could derive for the PE after the fault. Okay, and then the problem also asks you to determine the critical clearing angle. That shouldn't be the big deal, right? And yes, as this is easy. The first part is easy. Now you see you've determined the current. Once you know the current, right, you could find the total transfer reactance between, this is clear, between the internal EMF and the infinite bus. The other words, transfer reactance, you see, you understand the word transfer, right? It is the between in and out, okay, between the input power and the output power. So the input power is from where? It's from the internal EMF, and the output is at the infinite bus, right? Once you know the total reactance or the transfer reactance between internal voltage and infinite bus, so you can determine the transient internal voltage, or the E prime. So knowing the E prime, this is very important because this is the PE, right? This would define the PE before the fault, right? So this will define the PE before fault. Because this is the E prime before fault, this is the initial rotor angle delta zero. Okay. So the power equation, as we said, the P max is the E times V. V here is the it's a transfer between internal voltage and infinite bus at 1 and angle 0. This is 1, and the total, this is the PE before fault. This is the transfer reactance 0.65 sine delta. This is then 1.8 sine delta, right? So the initial ordering point, okay, it's the and is the point at which PE is equal to the PM. In this case, the initial power is the 0.8. Is 0.08. In this point, the PM and PE is equal, right? So you can see that why is it 0.8? Because the problem says that the generator is delivering zero point 0.8 per unit, right? So now you see that you can solve for the delta zero. The delta zero in this case is 26.388 degree, right? Or the radian in terms of radian is 0.46055 radian. Now you can see that we have to refer to the previous figure. You see that this is what we discussed, right? The delta max here it's another side of uh, the parabolic curve that would make that would make the PE equal 0.8 as well. If you see from this picture, right? This is the picture that how we get the delta max. Okay, the delta max that was the PM that was or PE at this point is 0.8. So you could solve for this point, right? You know the P max. Okay, so that's why you can see you can this is how we can get the delta max here. Okay. So the delta max is on the other side of the curve with the same value of PE to be 0.8, right? So this is the 2.681 radian. So now you could just substitute, right? In this case, the delta C is in explicit form. You could just substitute the right side of the equation, right, by the predetermined values, right? So you can find the critical carrying angle in this case by taking the inverse cosine of this cosine value, right? So you get the delta C at 1.48 radian, okay, and then you convert it back to TC, which is 0.26 seconds or 260 millisecond. Okay, so the critical carrying angle can be, if you draw this in the picture, right, you can see that this is the critical carrying angle at 84.77 degree. Okay, this is the maximum angle that is allowed. Okay, before the generator will lose the synchronism. All right. And yeah, for case B, the case B itself, you have to deal with this is the steps we have discussed, right? The step one is that we need to determine this is we have to redetermine this because the PE after the fault, right? The delta max is the PE after the fault. So the after the fault, you have to recalculate the total transfer reactance after the fault. Okay, so you have to find the X after the fault. How much is it, right? And then yeah, from that case, you know the X, assume that the E is constant. From the previous case, the E remains constant. So you could find the PE during the fault. This is the keyword, right? So once you know the PE during the fault, you could find the delta max. Okay, once you find the delta max, you find delta C, right? And once you know the delta C, you could find other variables, right? You could recalculate this in terms of a TC. That's not a big deal, right? So from the figure itself, from the system, if you see that once there is a short circuit at the middle of the lower path, once there is a short circuit at the middle of the lower path, the equivalent circuit. So remember what we mean by equivalent circuit. Equivalent circuit means that it has to be a complete path, right? So the equivalent circuit can be drawn in this case. You see this is an internal EMF E prime, and this is the reactance, right? This is the leakage reactance of the transformer, I suppose. No, it's a sum of XD prime, the subtransient, the transient reactance of the machine, of the synchronous machine, and the transformer, right? This is zero point 0.5. In this case, this is XG prime plus X of the transformer, XT transformer, okay? And in this case, since there is a fault at the middle of the lower path, right? So it is connected to the ground. This is the fault path. So the total reactance of the lower path, it's divided into two, right? Because this is a fault at the middle of the path, right? For example, if I introduce the fault at, for example, 30% at the 30% of the length, so you have to divide this correct I mean accordingly, right? This is so this reactance should be 30% of zero point 0.3, where this should be 70% of zero point 0.3, right? This is 0.09, this is 0.21, for example, right? If the fault location is changed to 30% measuring from the bus one, from the sending bus, for example, right? But in this case it's at the middle point, so it's just divided by half. Okay, it's clear, right? And this is on the right side is the infinite bus. All right. So in this case, okay, you can see that this is the delta transformation. Okay, we are trying to simplify this. Okay, because you can see from here, what you can see from here is that once you introduce the fault, right? The If you try to map with the original circuit, okay, we don't have you know we are trying to simplify, right? We want to model this in the Y circuit. Okay, we transform this delta circuit into Y. Okay, where you have the Y uh, at the junction, right? We can eliminate this, and you see you can do the transformation from left side to the right side, and then from this case it's easy, right, to find the transfer impedance between the two buses, right? So now you can see that from the equivalent circuit, you can see that, right, the transfer equivalent circuit can be done by the transformation. Okay, um, this is delta, and we change this to y. It should be correct, right? Um, to y. Okay, and is it clear, right? And I will leave you to check this. Okay, I think it should not be the problem. So you find the equivalent reactance to be 0.18. So you find the total equivalence reactance of this guy. Okay, this is the x2, what we call x2, right? This is the during the fault. So 1.8, okay, and you get the value of the power angle equation of 0.65 sine of delta. Once the fault is isolated, right? The fault is isolated, so you have just the upper path, right? So this is then point 2, where is point 2 in this case? Point 3, point 2, and point 3. Point 3 is here. This is just the the upper circuit, the upper circuit of the line between 1 to 2, because what? Because the lower circuit is isolated after the fault, right? So you can see that you get the third equation. What do we mean by second, third? You look at this chart, all right? This is the P1. This is PE1. But what we mean by this is PE2, and this is PE3, right? So in order to find the delta max, you have to deal with the PE2. Okay. So the PE2 itself, you take the you have to go straight to arc cosine of, what is this guy here? This is after the fault. Is it right or not? Let's see. It has to be, sorry, it has to be after the fault. I mis explained. Okay, this is must be, you have to deal with PE3. So you deal with this equation. Okay, from the picture itself, this is after the fault. Okay, the delta max is the corresponding point after the fault, because this is corresponding to the decelerating area. So you have to deal with this function, right? This is the 2.5628 radian. Okay, and once you know this, you solve for delta c. Delta c, you just substitute the value, the calculated value to the right side of the equation, and then we determine the delta c, the corresponding critical clearing angle. And I mean, from this point, right, you could also calculate the TC, the corresponding TC. But for this problem, the TC is not asked, right? So I hope this is clear. I think more or less clear. Okay, it's definitely hard at the first stage. Okay, because this is a huge subject and it's a little bit complicated, I would say, right? It's compared to the previous three chapters, right? I would say this is the hardest one. Okay, and I would suggest you to go through the lectures again if you don't understand, or if you have any questions. So I am more than happy, and I'm always ready to answer your questions, right? And that I think this is all for the whole semester, right? For the whole power system analysis of the course, right? For the after this, right? We still have some time left before we close. We come to the end of the semester, right? So the rest of the time, I would entertain your questions. So we would organize the what we call a live session. Okay, once you go through all the materials and you do the homeworks and you do the exercises. So only in that case, right? You could you could formulate your own questions, and you could discuss further, right? So I hope you all the best, right, to all of you, and then see you in the next video clip. Thank you.